Hello, everyone. Welcome to the third day of MLRW. Today, research work, which he did while interning at UNSW under Rohitash Chandra. So, we are glad to have you, Animesh. I hand it over to you.
Thank you,
Go on.
sir. Good afternoon, everyone. Uh, it's a pleasure to be here. So just let me share my screen. Yeah. So you can see the screen, right? Yeah.
Yes.
Okay. One second. Yeah. Good afternoon, everyone. In this talk, well, it's not as a talk; it's a discussion, and we will first begin with a very brief overview of what I'm going to talk, and I will be very quick because, as you can see on the left side, we have some bit of material to cover. But that does not mean that I will be skipping over things. Firstly, let's break down the whole title in detail. So. Memory capacity of matrix representations in neural networks. So there are three concepts here: memory capacity, matrix representations, and neural networks. We all know about neural networks, so we won't go into detail. So just reading after the title, few things must come into your mind. That is, what memory capacity are we talking about? That's how we're going to come to our first question. The whole discussion now is on question based. We will start with a very basic question, try to find its answer, and the whole talk in that aspect is self-contained. That is, I will present in the first slide what is my question that I ought to solve, and perhaps in towards the end, and I will finally present the answer to it. And in that aspect, it's self-contained. So hopefully you don't need any more information rather than, more than provided here. So before I say anything more, let me just give you a bit fair of warning that this is actually currently work under review. Hence, there might be few changes in the final work and perhaps in these slides too. But I'm actually not that worried about what would be changed or what's not, because the material that hopefully we will cover here in the next hour is not even the point of the talk. The point of the talk is not to show them what mathematics can do and or what are the results, but the point of the talk is to present a viewpoint which I had over past summer of neural networks. It is this viewpoint that I think is much more important and much more actually, you can say, insightful rather than giving you just a bland old mathematics and saying to you that this is how the memory capacity of a certain type of neural network decays and just learn this. Of course, that's not the point of the talk. The point of the talk is to present that viewpoint. What viewpoint I'm talking about here? Here, the viewpoint of neural network is of dynamical systems. So a dynamical system for our purposes is anything that takes inputs from the past and produces new output for the present. So for our purposes, that's the definition of dynamical system that we will go with. And I will then explain how that viewpoint is actually quite beneficial if you want to study neural networks using mathematics. Okay, so before I go into starting details, I want to be very clear that again, those people who are watching this are students, and I am also a student. So I don't claim any right for me that I know any better than anyone here. I'm not a preeminent expert in complex dynamical systems. So if any one of you have any doubts, you can ask me anytime. Either I will let you know what the answer to is if it is in my knowledge, and if I don't know the answer, then I will be very clear that I really have no answer to it. Because, well, there's no point in giving vague answers in mathematics. So okay, with that out of the picture, let's actually go into what we're going to cover. So let me give you a very broad overview of what we will cover. So in the first couple of slides, we will actually see what happens and what are the motivation for changing the representation of recurrent, for your purposes, a recurrent neural network stores vector-based representations, right? At each time you generate xt from wxt minus 1 plus b, and these xt for all time t are vectors. But what are the motivation and what are the benefits that one can have if you remove that constraint that vectors that the state at time t for a recurrent system should be a vector? That is, is it possible if we can put a matrix representations there? That is what the first content is, that capital Xn over small xn for representation. Capital Xn here is a matrix and small xn is a vector. Next, we will formally, from the first slides, we will then deduce matrix neural networks and who introduce them and what exactly how they work. And then we will go into a very brief detail of Fischer information. And this is where I hope those who are interested in information theory and related notions, they would find it very interesting. And in fact, the notion that Fischer information is, if you have a beauty for mathematics, then if you have an eye for mathematics, then you will definitely find the notion of Fischer information quite beautiful. And it is indeed quite beautiful, as we will explain. Then comes the notion of memory capacity, which will use Fischer information, of course. And again, this comes quite naturally if you understand the notion of Fischer information. And this is the point of beauty that I was talking about, that how Fischer transcendental in some certain sense that it leads to a notion of memory capacity. Then we will define Fischer memory curve. That is just how memory decays over time. And finally, we will calculate this Fischer memory curve for matrix neural networks as and hence in that sense, this whole talk will be self-contained. We will post a question in the first slides and then we will answer it, and hopefully by the final. So with that of the picture, you can see on the left side, we have an index, which is really highlighted at every point of the slide. So in that aspect, you know at each time where in the whole story we are. So we start with the question. In the middle part, we will develop the mathematics behind it. And in the final part, we will answer the question whether matrix neural networks have better memory capacity or vector-based neural networks. And well, I can say spoiler warnings. The answer is quite interesting, actually. And it's quite kind of counterintuitive. So if you get anything from this discussion is that you can understand the power of mathematics. Mathematics can get you places where normal intuition cannot. Hopefully, we'll see. So so now we discuss what are the motivation for shifting our representations from vector-based to matrix-based. That is, what is the benefits and what are the motivations for xn, capital Xn, that is a matrix, over small xn, that is a vector, for representation. So let's first begin with a very basic feed-forward recurrent system. Please note that I have not used neural network here. It's a feed-forward recurrent system, not a neural network. And I will explain to you, and I will give enough time to this too. That first of all, we know that a very basic feed-forward recurrent system works as in equation 1. Now you will, and it's quite natural to ask that actually this is not a neural network. This is a recurrent system. There's no non-linearity here. Non-linearities are part of neural networks. So in that aspect, this is not a neural network. This is just a recurrent system. It takes time, takes inputs from the previous state and produces output in the next. Then isn't it bad that the whole title of the talk is neural networks and we are in the first slide going into recurrent systems? To that question, I will say yes. In that aspect, the title of the talk is a bit misleading. But perhaps let me give you an analogy which explains why I have removed nonlinearity for me. So consider that a person drives. Person is given an opportunity to drive a Formula One car for 100 meters. So uh, when a person has finally drove that car for 100 meters, does that person is that person now a Formula One driver? Of course not, right? It's illogical to say that a person who just drove a Formula One car for 100 meters has is now a Formula One driver. That is the same analogy that we will use here. The thing is, driving a Formula One car is quite complicated. But the first step to driving a Formula One car is to actually finally learn how to drive a car, right? You cannot just not know how to drive a normal car and jump into a Formula One car. A similar situation is here. We cannot just jump into a very complicated situation that is feed-forward recurrent neural networks with nonlinearities when we don't even know the basic tools in a much simpler case, that we don't even know how to drive a very basic Maruti Suzuki rather than Formula One car. So that's the problem. We cannot just directly jump into nonlinear systems. We need to actually see what linear systems behave like. And in fact, if a lot of you might know that recurrent neural networks works best in the ReLU activation. And ReLU activation is nonlinear. Of course, it's nonlinear, but for positive inputs, it is linear. So working on linear systems will give you a somewhat of an insight into what a nonlinear network might work like. So that is the reason that we don't use in the whole discussion, we will never use nonlinearities for the ease of expression and for the ease of mathematical analysis. I do accept that that is a bit of a drawback, but you will see that how mathematics becomes a bit simpler. Perhaps if you have knowledge of advanced functional analytical tools, then you can please correct me, and I'm more than happy to be corrected that perhaps I could have used here nonlinearities and used those advanced tools, but unfortunately, I'm not, aware of those advanced tools and concepts. So again, this is just my viewpoint that I wanted to share. That's the whole point of the talk, right? So coming on back to our question, what happens if the input between layers xn is not a vector? What if we don't want the input between the layers to be a vector? That is, the representation between in each hidden layer is not a we don't want it to be a vector. But why don't we want it to be a vector? Because there's a lot of scenarios in physical worlds, like when studying human behavior and certain data sets, and more famous images and then parse it through. Why is it unnatural? Well, for example, a pixel surrounding a region of a face related to eye. So eyes and nose. If you're making a neural network for detecting nose in certain images of humans, then whenever you create such a neural network, you will always you will use CNNs or any advanced neural networks. What you will do is at the end, you will always use a flattening layer. And I hope anyone who has implemented neural networks always uses this flattening layers, which takes all the data that CNN has in its parameter matrices and then flattens it out into a vector. And there is a case to be made that such reshaping is inherently flawed. That is, when you reshape this matrix into a vector, then there is a certain loss of information. How that information is lost, that, for example, in a 2D image, you will have certain areas which is highly correlated with surrounding pixels. But when you flatten it out, then that correlation is lost, or that correlation is far away from the individual pixels, because you will then stack rows by rows by rows till you reach the whole columns. So in that case, there's a case to be made that such flattening of matrices can lead to loss of information. And this case is what leads us to a motivation that perhaps we would like to we would like to represent the hidden layer representations as matrices rather than vectors. And moreover, there are a few quite very interesting cases arising in literature in which it is much more natural and necessary to use inputs into inputs and representations in the form of matrices rather than vectors. One of them is heteroskedastic regression. It's a very typical example. In heteroskedastic regression, what happens is that you are given a time series in which the underlying distribution has a variance which changes over time. So you don't have at each point of the time, you have a distribution whose variance is in itself an unknown parameter. So variance changes with time too. For this purpose, a lot of literature uses symmetric positive definite matrix learning and all that. What we will discuss now is actually a generalization introduced by some authors in 2016. So, okay. So now I hope the motivation is clear for why it is much more understandable, much more natural, and much more necessary to use matrix representation in certain sense, certain conditions rather than vectors. Okay, and I missed the fourth point here. So the fourth point actually mentions higher order tensors. So higher order tensors are just matrix in high dimensions. So in a matrix, each element is a scalar. In higher order tensors, what happens is that each element is in itself a matrix. So in that sense, actually, a video is a third order tensor if the images are grayscale. So you can see if we can directly incorporate such higher order tensors into our neural networks, then it would be quite interesting to note whether they are any better than vector neural networks. And this is what we exactly cover up in the whole talk. So finally going to matrix neural networks. So a few authors in Gao et al. In 2016 first put forward the idea of matrix neural networks, in which the intermediate layers are matrices themselves. And how do they process these matrices? We will see using a bilinear transformation. A bilinear transformation is nothing but a transformation which is linear in both the variables. So and we will see how that also comes out to be. And also at the same time, there were a lot of authors, as I mentioned in the heteroskedastic regression, sorry. There were a lot of people who were using specific areas of such bilinear transformation in SPD matrix learning. SPDs are symmetric positive definite matrix learning, which are used in heteroskedastic regression heavily, among others. So at 2016, it was a very good time to be working on this to a certain extent. Yeah. So the authors Gao et al. In 2016 paper uses this transformation. So you can see it is a direct generalization of vector neural networks to matrices. The U, V, and B are the parameters here. In the equation 1 here, we had W as a parameter, which takes a state at previous time and converts into a vector for the state vector for the next time, plus this bias. So of course, W, if X, the state vector has a length capital N, then W has to be of a shape N cross N. Similarly, here what happens is Xn minus 1 is supposed of shape N cross M, capital N cross M. Then U transpose has to be of shape, yeah, I did not. So okay, they are of conformable sizes. Of course, output should be of shape N cross M2, and input is already a shape N cross M. So this U transpose will be of shape N cross N, and this would be of M cross M. And of course, B bias would be a matrix of shape N cross M. So you can see here we are actually factoring out our representation, parameters, which in the equation 1 we had a W. Now we have a U and V, and then a bias. So you can see this is how a matrix neural network works. So with this, the state at nth time step is retained as a matrix. At each time step or at each layer, you have a matrix representation rather than a vector. Moreover, the matrices U and V can be seen as representing the column-wise and row-wise features of the state, respectively. So what happens is U processes the columns of xn minus 1, and V processes the rows of x of U transpose xn minus 1. So in that aspect, well, it is again it is processing row by row and column by column, but now we have a representation which is a matrix rather than a vector. So such a network can therefore effectively process 2D inputs, and therefore reducing a loss of structure information present in flattening operation. So you don't need to flatten your two-dimensional inputs. You can process them as it is throughout the layers. Okay, so this is the equation 2 is the matrix neural networks, which we are going to talk about in detail now. So and a few examples of how they are used. They were used successfully and better than their vector neural networks of similar sizes in high frequency time series analysis and cyclone track prediction by some authors in 2016 and 17. So now let's. I hope everything is clear for matrix neural networks. It's a very basic network. There's nothing much more to it. U, V, and B are parameters here. B is still the bias matrix. V and U are now the parameter matrices, which we need to learn. And we will learn the usual gradient descent works on it. But we won't go into how they are learned and their learning criteria and all that. We have something else in our mind. Because we want to see what is the memory capacity of such a structure, actually. We want to see how this structure is better or worse than this structure in equation 1. So the question is, the memory capacity, as we will define now, is it better for a dynamical system in equation 1, or is it better in dynamical system in equation 2? We will see its answer towards the end. So let's now introduce Fischer information, because this is something we want a notion of information, right? So this is the notion of information, and this notion of information will lead us to notion of a memory capacity. So the Fischer information is actually just a way of measuring the amount of information that an observable random variable x carries about an unknown parameter theta, upon which the probability of x depends. Now, well, I can show you the definition of Fischer information, but I think that is not good enough for us to for our understanding. So you can see, well, there's very little to gain from equations directly. So what I can alternatively do is to give you an intuition of certain kind. So consider a random variable x, which is distributed as a probability distribution function p. P as in point 2, p is the probability distribution of x, and it is parameterized by a parameter theta. So parameter theta here is the parameters which parameterize the probability distribution. For a Gaussian distribution, you might remember that theta is a vector, mu and sigma. Yeah. So how can we find the information contained in a random variable x about the unknown parameter theta? Well, there are a few things to note here. Suppose I am given the probability distribution function p, which is parameterized by theta. Then if I change theta ever so slightly, then what can happen? Either the probability distribution would change very rapidly, that is, with small changes in theta, the change in p would be quite high, or the p would not change at all. Now, if p changes quite high, I hope you can understand this, that if theta changes quite high, then we can say for sure that x contains a lot of information about theta, because it's changing quite rapidly with theta. Whereas if p of x does not change rapidly with theta, that is, it remains flat with changes in theta, then we can say that probability distribution is x that does not contain much information about theta, because it's not changing much by theta. Therefore, the notion of information for a random variable x parameterized by theta can be considered in the way that how much a change is in the probability distribution of x given changes in theta. And this is the reason equation 3 is used. Equation 3 is the variance of the derivative of probability distribution. We use log for because it's much simpler. Yeah, it's much more analytical to study the logarithm of probability distribution rather than distribution themselves. So you can see in equation 3, what we have is a notion of information which is calculated by variance of how probability distribution is changing with theta. So if probability distribution changes much higher with theta, then we will say that it has x has much more information about theta. And if it does not change much, then there's not much information about theta in x. Or the notion of less information about theta in x can be alternatively said by we need more samples of x to actually determine what theta is. So that's what it means, and I hope that you can see now why Fischer information is a very natural way of defining information. In fact, so natural that if you and this is where the beauty part that I started with comes in, that it is such a natural definition of information of a random variable dependent on parameters theta, that there's a whole field of information called information geometry, which depends on Fischer information metric. So you can see how deep this notion is, and this is where the beautiful part comes in. So, and I hope I was able to portray to you how natural this definition is. That the rate of change of probability distribution with changes in theta. Okay, so if also now it happens that if it so happens that log of distribution is twice differentiable, then we can open up the square, and there would be some expectations which will go to 0. It's quite simple to see, and we will be left with equation 4. Okay, and one thing that I forgot to mention in the start is that, of course, I will have to skip over a lot of mathematics because I want to just portray the final equations that I get. So, okay, in that notion, the fourth equation is the case of equation 3 when log probability is twice differentiable. And we will see this in very detail. Now, one thing should occur quite frequently to you, that the theta here is a scalar. But most of the distributions that we know does not depend on theta, does not have one scalar, one parameter. For even the normal distribution, you have mu and sigma. So there's a case to be made that just one scalar variable would not work. So what we'll do, we'll use a vector of parameters. And this is what we do. When we have a vector parameters, then we use a Fischer information matrix. Again, it's very simple. It's just a Jacobian, if you are aware of it, of the log probability distribution. Or you can alternatively define as the ij element is this quantity. And you can see quite easily that the diagonal elements of Fischer information matrix are just the Fischer information for the Fischer information about the parameter theta I contained in X. So yeah, so if my distribution is Gaussian, then I would have a 2 cross 2 matrix because I have two parameters, mu and sigma. Okay. So again, the diagonal elements of Fischer information matrix is actually just the Fischer information contained in X about the parameter theta I, the ith element of the parameter vector theta. And we will see in the coming slides that this notion of memory capacity, this notion of Fischer information matrix is quite natural to produce a definition of memory capacity. And we will see that is quite natural again. Okay, so I hope everything is clear till Fischer information matrix. A lot of you already might have done the courses in this, but I hope I was able to portray you a new view towards Fischer information, which is quite natural. And if you're really interested, please read upon information geometry. It uses some really beautiful arguments about Fischer information metric and all. So yeah. So let's now come on to next notions that we will develop. We have already developed a notion of Fischer information. We now know a notion of memory matrix neural networks. Now different definition of it, if whether he or she works in probability or whether in functional analysis. So for example, let me give you a functional analytical definition of memory capacity. This definition of memory capacity is used by two authors, Baldi and Varshain, in their 2019 and also in 2020 papers. And this is a very, again, it's a very natural definition to us. What these authors define memory capacity of a neural architecture, this is S, fractal S, that does not matter. For the memory capacity of a neural architecture can be defined as the largest value of K, such that there exists a function f in the space of all realizable functions by the S, which, provided with the input label set this, remembers them correctly. So what this means is that it is this memory capacity defined by these authors is the largest size of a data set which the architecture can remember exactly. I hope. Yeah.
Yeah. So I'll read it out to you.
Yeah, please.
In NLP, we use cosine similarities to understand similarities of word vectors, and it is intuitive. How could matrices be useful in such NLP tasks, or these networks exclusive for images?
Yes, so the similarity here, yeah, so what I can think of is so one can actually use in NLP, you use similarities, right? Perhaps you can learn similarity functions yourselves by using these type of neural networks, matrix neural networks. Your input would be an n cross n square, n cross n square matrix, where each element. Okay, so you have certain. So you have certain words on which you want to find the similarity. So you can, in fact, pass this into an n cross n vector, and then your output can be whether the similarity learned by them in the form of similarity matrix. That is, So the similarity matrix, whether if you want to learn a certain similarity measure, then you can hopefully use it in this way. I'm not sure how if it is used in anywhere. I'm actually not an expert in NLP, so but perhaps that is one way which can happen, in which one can learn that. I hope it is understandable what I meant by. Okay, so you have n words, and you transform it into a matrix n cross n size, and then hopefully you can learn the how all these whether ith part is related, how much ith part is related to the jth part, and then you can find it a very nice matrix of some sort. Does that answer your question? Or I do accept that I'm a bit vague because it's not in my
yeah, he says
capacity.
yes.
Yeah. Okay. Thank you. So let's resume. So the two authors here, Baldi and Varshain, they defined memory capacity of a neural architecture as the largest size of the data set which the neural network can remember correctly. So what is that biggest size and how it can remember correctly? Well, if there exists a function in the space of all realizable functions by S, because any neural network is just a function approximator. It learns function. It is a universal learner, right? So it can learn any function given enough time and enough neurons and enough training time. Of course, there are some constraints there, but let's not get into it. So yeah, that's the memory capacity that these two authors work with. The largest size of the data set, which the neural network can remember correctly. Now, the thing is, this works very well for input label set here as the following is a set, the pair of x1, xi, and yi. But what happens when actually you read their own paper, Baldi and Verschainen, it becomes extremely complicated very quickly, because this is a very functional definition, and well, functional analysis uh, uh, is a bit of a difficult field, right? So because it has a lot of concepts. So due to that nature, the functional nature of the definition, it becomes extremely difficult to derive the bounds on this size k for a matrix neural network. Uh, no one has tried as such, but at least in my experience and the second author's experience, it has been a very difficult. It is very difficult to derive bounds on the memory capacity as defined by Baldi and Verschainen for matrices for neural architectures which are matrices rather than vectors. So even in their own paper, as I said, it becomes complicated quite quickly. So what can we do actually? So there are a few things that we can do. If we simplify our model enough, then we can see that there can be a probabilistic definition of memory capacity. The definition here by Baldi and Verschainen is a functional definition. It takes it demands an existence of a certain type of function in the space of realizable functions. What if we don't want that? We in probability in information theory, we have a probabilistic notion of information. Cannot we use that to find a notion of memory capacity? And this is what we will do now. It will turn out that under certain some circumstances, the probabilistic definition that we will introduce is much more better, much more manageable than a functional definition for matrix neural networks. And actually, the notion of probabilistic memory capacity is a lot simpler for vector neural networks. And well, simplicity is lost when we go from vector to matrix neural networks using probabilistic definition, but it's manageable enough that we can work through it. So now we will introduce a probabilistic definition of memory capacity. We don't want to work with a functional definition because, well, it's we are not experienced enough in functional analysis to deal with certain kind of big questions right now. So we now introduce Fischer memory curve. This is defined actually. Okay, so let me now introduce what exact dynamical system we will study. In equation 2, long back, we said that we will prove whether this equation 2 has better memory capacity than equation 1. But the thing is, to introduce a probabilistic nature, we need some source of noise, right? We need some source of randomness, which is not present here. Okay, so yeah, the notion of probabilistic nature requires a source of randomness, which is not present in equation 1, neither in equation 2. And this is the reason we need to add some noise into our equation 1 and equation 2 to make them probabilistic. And this is what we do now. Now we study this matrix dynamical system, where xt minus 1 is state at t minus 1, xt is the state at t, and w is a matrix which transforms the input st to, or not transforms, it connects the input scalar input st to the state at time t, and zt is a matrix Gaussian noise. Okay, so input here is a scalar. Please note that very clearly. However, input is a scalar. The representation stored are still matrices, and a source of noise is the capital ZT. The capital ZT is not a random vector. It is a random matrix actually, and random matrix has some unique properties, which well, a random Gaussian random matrix is defined by this. Don't think you need to well, you can go to Wikipedia. It has a very nice article on it, but I don't think that's much more necessary right now. But just imagine that instead of a random vector, you have a random matrix whose each element is a random variable. Okay, so and we use we have a normal Gaussian in which we have zero mean and identity variance. We use the similar one here: zero mean matrix, and identity variance. So a Gaussian random matrix, which we use here in ZT in equation 6, the source of noise, which will induce a probabilistic structure, then is of zero mean and of identity variance. Okay. So here epsilon1, epsilon2 are small constants, which do not matter much actually for our talk currently. Okay, so I hope this structure is clear. So input is scalar. Please note that. Of course, you might say that this is quite contradictory to what I said earlier, that input would be a matrix itself. But the thing is, we want to mathematically study things, and that's where the F1 analogy comes in. That we want to study firstly something which is very simple, not something directly which is very complicated. Perhaps I could have added here another input to this to make it more similar to recurrent neural networks, but that would be extremely difficult and would not be possible to cover in a talk too. So we just deal with a very small scalar input. It is connected to this state by this matrix W, and a noise is added using the Gaussian random matrix. And the Gaussian random matrix in itself has zero mean, has no correlation with its along its columns, has no correlation between its rows. So it's a very simple random. In fact, it's just that each element is a normal unit Gaussian, simply. So even this is not important, that it is a Gaussian random matrix, at least for our talk. I use this for in our work because for calculation purposes, which I will also not discuss here, but I think it's interesting enough. So I hope structure 6 is clear. Now, it is important to note that the input, the same thing which I just mentioned, that the input here to system 6 is actually a scalar, not a matrix. And this is the simplification talked about in the previous slide. Where in the first slide I talked about simplification of our problem. We want to simplify our problem to a certain extent that it becomes penetrable. Now, what happens? Now, why exactly have I chosen it in this way? Actually, what happened in there's a very nice paper in by Ganguly and others in 2008. In which they studied a similar structure, but of course, it was a vector representation based. So they had xt was a vector, xt minus 1 was a vector, w was a vector, and zt was a Gaussian random vector. And there was no u and v, there was just a matrix w, just like in equation 1 we discussed. We will discuss what they did too in the coming slides. So now we come up to our first aim to define what a memory capacity can be for such a network. So our aim right now is to find the information contained in state xt and in the matrix xt at time t for the input signal at k time steps prior. So since at each time xt is receiving input as st, a scalar input, but at current time t, we do want to understand that how much information current state xt has about an input which appeared k time steps prior, where k can be anything. For example, 100 time steps prior, how much information does xt currently have about that input? What about just 2-3 time steps prior? How much information matrix xt, state xt has about that input? And you can now see that how the notion of memory capacity is kind of forming right now. That the information contained in the for the past random past input, sorry, in the current state. Well, that's what memory capacity should be, right? And that's what we will now develop more deeply. So now that we have made our system 6 and a probabilistic structure from a functional, so we have jumped from functional to probabilistic structure. Now let's finally define what the Fischer information and what's the notion of information that we will use here. So now how can to define to use Fischer information, we need parameterized probability distribution. So we need to first construct a parameterized distribution. And what other way is there to, so that you see now the point of why we take scalar input, because we now find the distribution of xt given the past inputs. And this is what is portrayed here. If we collect all scalar inputs sk for all times k, where k can be any time, into a very long vector boldface S, then our aim, which we define here in the boldface down below, would just reduce to finding the change in the conditional distribution of xt given this all inputs S, where when S is altered by a very small amount. So what I mean by this is that okay, so when we constructed our vector very long vector boldface S, this is the vector of all inputs seen in the previous line. That is yeah, so it's all the inputs, scalar inputs into a very long vector boldface S. Now what we want to find is how much probability of current state xt depends on this vector. That is how much and what is the probability of seeing the current state given all the previous inputs. That is what is portrayed by probability of xt given S. Now, since we wanted to find information contained in xt at time t for input all these previous inputs, then what we need to do is to find how much the current state xt is changing when we change our current when we change our input vector by a very small amount, delta S. So our aim now is to find the change in probability distribution, change in this conditional distribution, where conditional on the previous inputs, when the previous input vector is altered by a very small amount, delta S. So we want to do that now. So what this means is that we need, again, we want to find how much change in conditional distribution is happening when we change our input vector. So we need actually a notion to find some sort of difference between two probability distributions. One is probability of xt, conditional of probability given all the previous inputs, and one is the conditional on the previous input vectors plus a small bit of change. And what is there a better way to find difference between two statistical difference than relative entropy, right? This is a very basic notion. The difference between two distributions can be captured very nicely by relative entropy. So since our aim was to find how much change is happening in this conditional distribution in point 1, when certain changes happen, then we can just use this relative entropy between these two changes in equation 7. And this is what we do now. And when one actually calculates between the Kale divergence, this is also Kale divergence, it's more famous by relative entropy. So when one actually calculates the relative entropy between these two distributions in 7, it can follow from Taylor series approximation actually that it would be approximately equal to the equation the right hand side here in the equation 8. Note that it is approximate actually, and but we don't want this approximation, right? We actually don't want some uncertainty whether it is exactly equal or just barely equal. And okay, looking more deeply onto right hand side, what we see here is delta S transpose and delta S, which we know is the previous input vector, but J is the Fisher information matrix. And and the Fisher information matrix, and what this information is talking us about. The information Fisher information matrix JS here is the information contained in the current state about parameterized by all the previous inputs. And I hope that tells you that this is. I hope that you can see now how we are going to construct notion of memory capacity, because we now, if we calculate JS from equation 8, then we have a notion how much information is contained in current state given all the previous inputs, or sorry, how much information in the current state is there for each of the previous inputs. And that is a very good notion, I think, or it is indeed good notion, but it's not good right now because we have an approximation. We can calculate on the left hand side through using certain things we will see in the next slide. But if it's an approximation, then it won't be that good. So what we do here, actually not we do, it is fortunately enough, that's why I wrote fortunately enough, that if the distribution of xt given the previous inputs is linear with S, that is the mean of this distribution, P in equation 1, the mean of this distribution is linearly dependent on S. That is just some scalars multiplied with each components of S. Then this becomes an equality. The other things which I have not written here, they all goes to 0. So then this equation 8 becomes an equality. Now, since this happens only when it is linear with S, then and if I want to use the exact notion of we want to use exact notion in equation 8, not approximation, then it must happen, right, that this mean of pxt given S is linear with S, and exactly that happens in the next slide. Actually, okay, so if you continue with this way and then you calculate both sides, you might have an approximation here, but one can calculate this part, expectation of this given previous input, and actually you can see that it's just linear with us, and this is what is portrayed here. So there's lots and lots and lots of steps which I have missed from previous slide here to here, but I think it's necessary to actually complete this in time. And yeah, so after a few pages of mathematics, one can actually derive this form of information, Fisher information matrix, JS. So again, just to repeat, just to make things clear, the JS is the Fisher information contained in the current state matrix about all the previous inputs. So yeah, so this is the closed form of this matrix. And you can see it's a very complicated, okay, so again, if it would be a scalar, of course, it's a matrix, and Jij is the ith and jth component of that matrix. So it would be a scalar, and that's why it's a trace here. And this trace is of a very complicated matrix. Trace is just the sum of the diagonal terms. We all know that, but calculating that is extremely difficult because we have these derivatives, and then we have these infinite sums themselves of matrices, not of scalars. These are all matrices. So it would become complicated quite quickly. So we now finally actually come to what we get by Fisher, what we mean by Fisher memory curve. Given that we have developed this Fisher information matrix for, okay, so equation 9 is the Fisher information matrix for this system in equation 6. Please keep that in mind. We have now finally derived the Fisher information matrix for a matrix dynamical system which stores matrix representations. So that is very important. So now that we have done this, we are coming close to a notion of Fischer of memory capacity. Now, what is Fischer memory curve actually? We are given this. Fischer memory curve, given the Fischer memory matrix, is just the diagonal elements of Fischer information matrix. Seriously, it's just that simple. It's the diagonal elements of Fischer information matrix. And why is it diagonal elements? Precisely because we, as I said earlier, that diagonal elements of Fischer information matrix are just the Fischer information of those parameters. JII is the Fischer information of SI. That is the input at ith step prior. So JIIS would be information contained in current state about an input which appeared ith time steps prior. Let me repeat it again. The diagonal element of JS would be information contained in current state of an input that appeared ith time prior. So you can see now we are getting very close to memory notion. So if FMC is defined in this way, that the diagonal elements of the Fischer information matrix, okay, so a Fischer memory curve is a curve between the diagonal elements and the diagonal index. So x-axis would be your I, the diagonal elements, and y-axis would be JII, what is the element stored in that slot of Fischer information matrix. That means the diagonal elements of the Fischer information matrix, which denotes how much information current state has about the ith past input, is defined as the points of this curve. And we will plot this curve, as you will see in the final slide, where we finally conclude our lecture or our talk discussion. So calculating the FMC of this part, this is the Fischer information matrix of the dynamical system, which with matrix dynamical system, which we mentioned previously. We get this. So this is just the diagonal elements. You can see. Again, I'm skipping a few bit of mathematics to conclude on to this, but you can take my word for it if you wish to. So, so the ith element is this. Is a trace of this very big long multiplication of matrices. And keep this in mind that sigma and psi themselves, as shown here, are infinite sum of matrices, as you can see. So it's quite a scary quantity. Now, a very striking result happens right now. That is, as you can see, JI is the information contained in the current state about ith past input. But actually, it does not depend on the ith past input. We have complete freedom from that. There is no SI here, as it was a derivative, as you can see in equation 9. The derivative actually cancels that out. As you can see, the SK here, the past inputs only was present in this MS, and we were taking derivatives of it. And since it is linear, and so that derivatives got cancelled out. That is the reason we don't have so a memory capacity of a matrix dynamical system as defined in previous equation is actually independent of whatever the input was. It is just dependent on your parameter matrices, and that's a very striking result, and not that striking actually. It is quite expected because we are using Fischer information, and to calculate Fischer information matrix, it turns out that there are derivatives, and which cancels out since our mean is linear with us. And actually, this is the reason why this equality happens. From here, we had an approximation, but we now here have an equality. It happens because of this reason, because MS is actually linear with us. And this is what we talked here in the last point. This approximation becomes an equality if and only if this expectation of the mean of the conditional distribution is linear with us. And in fact, as you can see, it is linear with us. MS, in fact, is the mean of the conditional distribution. So it's linear with us. Finally, so we calculated the Fisher memory curve. This Fisher memory curve, to repeat it again, is just the how much information current state has about the past inputs. And as we see, we can now develop a notion of memory capacity with this. The FMC of a dynamical system, as we saw earlier, tells us how much information the current state has about individual past inputs. Uh, as we saw here, GI, it was exactly this, how much information current state has about ith past input. And with this, we can now develop a notion of memory capacity. We can just sum over all the i's. Then what will that give us? It will give us how much information the current state has about all the past inputs. And this is exactly what we would mean naturally by memory capacity. How much do I remember currently, what happened to me in the past? And how much information do I have in my brain about what happened in my past? This is exactly what you mean by Fisher of memory capacity. And this is exactly what we do now. So you can see, and again, this is not what we have developed. This is borrowed from this author's 2008 paper, but we have extended it into a much more general scheme of matrix neural networks. The memory capacity of a system with FMC JI is therefore just the sum of all those JIs. So how much information does current state has about all the past inputs, whether it was infinitely far away or whether it was just in the one time step prior. So now if we calculate this for equation 11, we have JII for equation for a matrix recurrent network. For a matrix recurrent network in equation 6, we have this as its Fisher memory curve. Then we can calculate its memory capacity as this is in equation 13. The memory capacity of a matrix representation network as defined in equation 6 is just this, the sum over all of this of its Fisher memory curves. We finally get this, and this is the notion, this is the closed form equation of the memory capacity that one would mean by memory capacity. So finally, we have a notion of memory capacity for a matrix recurrent network. In fact, we have an equation for memory capacity for a matrix representation network. Now, can we calculate this? Can we calculate this? The answer is no. It's extremely difficult to calculate this. Why is it extremely difficult? Well, first of all, you have an infinite sum of scalars. Second of all, you have trace of a matrix, which is very complicated. And then you have two matrices here, sigma and psi, which in itself are infinite sums of matrices, and not just infinite sums, they are inverses of them. You can see we need to calculate its inverse, and well, it's extremely complicated. And that's the notion. That's what it's the last point mentioned. This is not easily computable. Then what's the point of all this when we cannot actually compute all this? Now, before answering whether we can calculate all this or not, let me bring you back to the question that we had in the start. We wanted to compare the memory capacities of these two networks. The network in equation 6, which dealt with matrix representations, but we never actually introduced a similar analog. Let me go back to equation 6. Yeah. So we have so far completely defined what we mean by a memory capacity of a recurrent system as in equation 6. But how can we compare it to a vector system? We don't have any vector system, and I did not introduce a similar vector system. So that's what we do now. First of all, we now secondly introduce a vector system, but we won't go into as details as we have done here to calculate its Fisher memory curve and then its memory capacity, because this is done by this author actually. Ganguly et al. In their 2008 paper has already calculated the Fisher information, memory capacity of such a dynamical system. So you can see here it is exactly same as in equation 6, but it's just for vectors. So there's no u and v's. It's just for vectors, w xt minus 1, and st is still the scalar input. We connect the previous input. It connects the current input to the current state, and zt is a Gaussian random vector. Now the thing is, we don't need to calculate its memory capacity because it's already done by this author, and so our work is much more simplified. So we have already calculated in equation 15. I hope equation 14 is clear. Again, to repeat it just one more time, that we computed memory capacity of a matrix representation network. How did we calculate that? We first made our matrix representation system a probabilistic structure by adding Gaussian noise there. And we do the same thing here. We add Gaussian noise here, and then we have a recurrent system which is now probabilistic in nature and deals with vector representations. Then we can calculate its memory capacity, and we get equation 15. You can see how simple equation 15 is compared to what behemoth we have created in equation 13. And the label of equation 13 is also suitable. It's 13th. It's quite difficult to calculate this. It is actually impossible to calculate this. Because I've tried, and all the time I using a lot of algorithms, but I always got nans and all, because it's just too much to calculate so many infinite sums. It always crosses over the boundaries of memory and all that. So anyways, we will see how still we can calculate this, and this is very ingenious part of the author in their 2008 study comes in. So we have now two quantities which we want to compare. We have the memory capacity and equation 15 of a vector representation based system, and in equation 13 we have memory capacity of a matrix representation system. We want to compare equation 13 to equation 15, and if we can do this, then again, j dot vec and j dot mat are scalars. Please keep that in mind. Of course, they would have to be, because they are memory capacity, right? Memory capacity would be a scalar, and this is in fact a scalar. So we want to compare just two real numbers. Actually, that's it. But these real numbers are calculated through a very gruesome process, and gruesome it is in equation 13. Not so much in equation 15. So now we finally calculate these. Now, again, there are a lot of steps which I will miss, but again, we are overshooting our time, but I will go quickly, just 1 or 2 slides are remaining. So however, the memory capacity in equation 13 simplify. Okay, so in equation 13, the form which we have in equation 13 is very difficult to calculate. Everyone would agree with this. Now we can actually make this simpler if we assume a very, very basic assumption that if we assume our matrices, parameter matrices, to be normal. A normal matrix is that matrix which commutes with its transpose. A very basic assumption, again, well, basic for the mathematical purposes, but one can argue that this is not realizable in real life, but again, we are dealing with very basic notions. So if we assume that, then what we have is our equation 13 and 15, both of them actually simplifies to a lot extent. But again, if we want to compare equation 15 and equation 13 under similar circumstances, if you want to compare them under some assumptions, then we must use same assumptions for both of them. Because if we take one assumption which suits much more equation 13 and not equation 15, then that would be problematic. So we assume a very basic assumption that parameter matrices are normal. That is that the parameter matrices commute with their transpose. How would this assumption translate into matrix recurrent system? It would just mean that U and V are normal. That is, U and V, both of them commute with the transpose. And in vector recurrent system, that means that W commutes with its transpose. So in that sense, we are using the same assumption. U and V plays the same role as W in vector representation system. Yeah. So if we assume that these matrices as normal, then we are using the same assumption on both equation 15 and equation 13. And this is what we want to do. We want to compare them. Okay. So, okay, so we are on the last slide now. The resultant expressions for respective memory capacities under this assumption is actually still not simple. So you can see, even after so many assumptions, so many simplifications, the memory capacity is still very, very difficult to calculate. So we are under a very strict assumption, actually, that parameter matrices are normal, which of course it might not be when you finally train your recurrent network. Perhaps it will happen that it's not normal. So it won't fall into this analysis. But still we have to, because, well, we want to actually get somewhere with our notions of memory capacity. So after assuming this, even still, again, I'm not going to show the final expression. The final expression for this whole discussion is equation 15 and equation 13. More so equation 13, because equation 15 is already present in literature. This is our work in equation 13. So calculating these two are still difficult. If we assume normal matrices, they are still difficult. But now what? Actually, the thing is, we can calculate it still using computers. The form of equation 13 and 15, when under the assumption of normal parameter matrices, is still very long. It's still very hard to calculate, but it's at least calculatable. It's not that it's infinite sum of infinite sums. It is somewhat calculatable. And that's what we do now. So now I'm going to show the graph, which is the Fischer memory curve of both matrix representation system, as in equation 6, and vector representation system, as in equation 14. So that would be the Fischer memory curve. And again, one thing, let me just get back to you. This is the final slide, and we will conclude this. So the total memory capacity we defined as the sum of individual points of Fischer memory curve. What that means is that total memory capacity is just the area under the Fischer memory curve. And that is a very good thing to calculate. Well, you can calculate the area under a curve given you are given a curve. So if we have a Fischer memory curve of a certain dynamical system, what we need to calculate is just the area under its curve. And that's what we do now. We will calculate this scalar is just the j dot mat is just the integral or sum as a discrete integral of a Fischer memory curve of a matrix dynamical system, and equation 15 is just the integral of a Fischer memory curve of a dynamical system in equation 14. And calculating those curves, we get this. So there are a lot of curves here. The continuous curves are for vector representation systems. The lined curves are for matrix representation systems. These 100, 400, 900, 1600 are the neurons. So for each number of neurons, you will have a different dynamical system, and for them, they will have different capacities. As you can see, the vector representation system has a very nice asymptotic to one Fischer memory curve. And what will be its total memory capacity? It will be just the area under this curve. What we see here now, this is the result of the whole discussion, that the total area under the curve for vector representation system, which is represented by this continuous line, is higher in all cases and in all similar cases than the matrix representation system. And this is quite striking, actually, that the matrix representation system, even after doing such a great job at preserving the local information around the pixels and all that, actually has bad memory capacity than their vector counterparts under certain assumptions, that the assumption is being normal connectivity matrices. So this is striking. And in fact, more striking to this is that the memory capacity of a matrix representation system with 100 neurons is much more than the capacity of 400 neurons. So this is the result of the talk. That actually, it's of course, I hope that it was counterintuitive to you too, that a matrix system should, by the structure, should have a bit more memory capacity, because it's storing a lot of things, and it's preserving the local information around the pixels of the as matrices. But it's not actually, and that's the result of the talk, that memory capacity of a matrix representation system is actually bad. And in fact, this is not proved just by looking at the graphs. We proved that the maximum bound on memory capacity of a matrix representation system is actually lower than the bound on this a vector-based representation system. So yeah, that was the whole point, that matrix representation systems counterintuitively have bad memory capacity than their vector counterparts. And this is the conclusion of the whole talk. I hope you liked the talk. Is there any question, Shrey?
No, there seem to be no questions.
Okay.
So yeah, thank you, Animesh, for the enlightening talk, and
Yeah.
best of
Thank you so much.
luck with your work.
Yeah, thank you so much.
Yeah. So, guys, we also have another session from 3 with Dr. Amit Sethi from IIT Bombay. So, tune in. And now we are going to end the session. Thanks
Yeah.
again.
Yeah. If anyone has questions, they can. I think a lot of people are from our batch, so they can always contact me. I hope. I mean, if they have some better ideas or some doubt, well, not doubt as such, but if they have better ideas or perhaps scope for future work, I'm always looking forward.
Yeah.
Okay.
Okay.
Okay. Thank you, everyone.